Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International GCSE Chemistry Paper 1 CR for January 2021. This is the part 1 video. I'll put the link to the part 2 video below in the description box. Let's begin with question 1. Question 1 says, the box lists some substances. We have air, bromine, carbon, copper, glucose, nitrogen, oxygen, sulfur, and water. They say, choose substances from the box to answer these questions. Each substance may be used once, more than once, or not at all. The first question asks, name a metallic element. The only metallic element here is copper. And the next part says, name a compound. Compounds are substances that have at least 2 atoms from different elements. So I chose glucose as well as water. Next they say, name a mixture. Among the substances given here, only air is a mixture because air is a mixture of gases. And then they say, name an element that is a gas at room temperature. Again, it's only oxygen or nitrogen that are gases at room temperature. Part E says, name an element that forms a basic oxide. Basic oxides are formed by metals. When metals react with oxygen, they form metal oxides. So copper oxide would be a basic oxide, and therefore copper should be the answer. Part F, they say, name 2 elements that are in the same group of the periodic table. My answer is sulfur and oxygen, because they both belong to group 6 of the periodic table. So this brings us to the end of question 1. Let's continue to question 2. Question 2, a student does a chromatography experiment using ink 1, ink 2, and 3 known dyes A, B, and C. The student uses water as a solvent. The diagram shows the student's chromatogram. Now this is the chromatogram showing the results of the experiment. We see the pencil line where the dyes were placed in the beginning, as well as the ink. And we see the solvent front, the place where the solvent had moved by the end of the experiment. So when we observe the results, we can see ink 1 contains dye A, as well as dye B, because this is in here and that is in here. However, we can see that this dye is not identified because it's not present in any of the 3 dyes. We can also see that dye C is absent in ink 1 as well as ink 2. So the question asks, deduce what conclusions can be made about the composition of ink 1. When we observe the results again, we can see, again, like I said already, ink 1 contains dye A as well as dye B, but this one here is missing. So I said ink 1 contains 3 dyes. There is dye A as well as dye B. However, it contains another dye which is unknown. This is the dye it contained, but we do not know because it did not correspond to any of the 3 dyes used. So I said it does not contain dye C as well. In part B, give one conclusion that can be made about ink 2. Ink 2 was not separated into specific dyes, so we can conclude that it did not dissolve in the solvent that is used. So here I said ink 2 is insoluble in the solvent used. Next they say, suggest how the student could change the experiment to find the composition of ink 2. Again, to take you back to the experimental results, we can see ink 2 did not leave the pencil line, and that shows you it was not separated into individual dyes, and therefore it was insoluble, so we could change the solvent in order to allow it to be separated. So repeat the experiment using a different solvent. In part C, calculate the RF value of dye C, giving your answer to 2 significant figures. If we go back to the experiment, the RF of dye C is going to be the distance moved by dye C divided by the distance moved by the solvent. So this distance was 5.5 and that was 8.0, and therefore my RF value was 0.6875, but to 2 significant figures it was 0.69, and that was my answer. So this brings us to the end of question 2. Let's continue to question 3. Question 3, crude oil is a mixture of organic compounds. Most of these compounds are members of the same homologous series. State the name of this homologous series. We know that crude oil is a mixture of alkanes, so we can say the homologous series is alkanes. In part B, they say, an industrial process is used to separate crude oil into fractions. The process depends on a difference in a property of the fractions. What is this property? Substances present in crude oil are separated into different fractions using the difference in their boiling point. So my answer here was A. Down here they say, the boxes give some uses of fractions and some names of fractions. Draw one straight line from each use to its correct fraction. So beginning with fuel for airplanes, kerosene is what they use in airplanes. And then in ships, they use fuel oil. In surfacing roads, they use bitumen. However, diesel can be used in buses as well as normal cars, and gasoline can be used in cars. Moving on. In part C, they say, fuels obtained from the fractions may contain impurities. Explain how the combustion of a common impurity in fuels may cause an environmental problem. The common impurity is sulfur, and when sulfur is burnt in the presence of oxygen, oxides of sulfur like sulfur dioxide are produced, and when these interact with water, they can produce acidic water or acid rain can be formed. So I said, sulfur is a common impurity in fuels. Combustion of sulfur produces oxides of sulfur, like sulfur dioxide, which if released into the environment, dissolve in rainwater and react with it to produce acid rain. This acid rain changes the pH of the soil and water, leading to the death of microorganisms, aquatic animals, and plants. In part D, some of the fractions contain long-chain molecules which are not very useful. Give the name of the process used to convert long-chain molecules into more useful shorter-chain molecules. The process of converting long-chain molecules into shorter ones is called cracking. In cracking, a long-chain alkane is converted into a shorter-chain alkane as well as alkenes. Down here they say, give the catalyst and temperature used in the industrial process to convert long-chain molecules into shorter-chain molecules. In cracking, the catalyst used is silica, or you can say alumina, and the temperature is 600 to 700 degrees. The next part says, when carbon-13, hydrogen-28 is used in this process, 3 different molecules are formed. They want you to complete the equation for this reaction. Now remember, they've given us one product molecule, which is this. This is octane. So if octane has been formed, it means we are left with 5 carbons. And this one here is an alkane, so the other products must be alkenes. Which 2 alkenes are different that can be made out of 5 carbons? Those are propene as well as ethene. So this brings us to the end of question 3. Let's continue to question 4. Question 4. When iron is left in damp air, rust forms on its surface. State the chemical name for rust. Rust is called hydrated iron 3 oxide. You have to include the word hydrated to show that it contains water. The next part says, explain how a barrier method prevents rusting. A barrier method includes painting, coating, and so on. So when iron is painted, the metal is protected from being exposed to oxygen as well as water, so rusting will not take place. So I said, this method involves coating, painting, or greasing iron. This prevents the metal from directly coming into contact with water and oxygen. Therefore, rusting does not occur. In part B, a student uses this apparatus to find the approximate percentage by volume of oxygen in air. So the setup is as below. We can see a graduated glass tube. We see water. There is damp iron as well as a rubber band. So in here, there is going to be air contained, and therefore oxygen must be present as well. So on the next page, here they say, this is the student's method. Place a graduated glass tube into a beaker of water. Place some damp iron wool and a rubber band in the top of the tube. Record the reading of the water level in the tube. Leave the apparatus for a few days, and then record the reading of the water level again. The diagram shows the reading at the start and at the end of the experiment. So here we can see at the start, there is less water in the tube, but at the end, there is more water. This shows that the volume of air has decreased and therefore water has moved in to fill the void. So we can say the change in volume is due to oxygen being used up by iron as it rusts, and therefore the volume of water inside the tube increased. So here they ask, use the readings to complete the table, giving all values to the nearest 0.5 centimeters cubed. So the reading at the start was 20.5, and the reading at the end, if we can see, this is going to be 30, 31, 32, 33.5. So that's my answer. And the difference is going to be 13.0 centimeters cubed. This is the volume of oxygen used. Here they say, the student uses these results to calculate the percentage by volume of oxygen in air. Suggest why her calculated value is lower than the expected value. If we expected a higher value, it means we would expect the volume here to be higher, and that means more oxygen would have been displaced. However, if less has been displaced and therefore we have a lower value, that means the oxygen did not get used up, so we would have used excess iron in order to remove oxygen by making it react with iron. If iron was the limiting reagent, then oxygen is going to be left. So I said, probably not all the oxygen reacted with the iron, or probably the iron wool used was not in excess to ensure that all the oxygen got used up. So any of these would earn you the mark that was awarded here. Moving on. The student repeats the experiment using the same apparatus. These are her results for the second experiment. The volume of air in the tube at the start is 80.0 centimeters cubed. The reading at the start is 20.0 centimeters cubed. And the reading at the end is 35.5 centimeters cubed. So we are going to use these two readings here to find the volume of oxygen used up. And again, remember, they wanted us to use the results to calculate the percentage by volume of oxygen in the air. So we have to find the volume of oxygen used, divide by the volume of air at the start. So oxygen used is going to be that minus that, which gave us 15.5. And the percentage by volume is going to be 15.5 divided by the initial volume of air, which is 80 times 100. And that gave me 19.4%. And that is my answer for question 4. So this brings us to the end of question 4. Let's continue to question 5. Question 5. A student uses this apparatus to investigate the effect of heat on different solid metal carbonates. So there is a metal carbonate here and it's being heated inside a boiling tube. Some gas comes off and is delivered into lime water. Every time you see lime water, think of carbon dioxide. And anytime you see a metal carbonate being heated in a test tube, you should think of CO2 being produced, and therefore they're testing for carbon dioxide gas here. So here they say, this is the student's method. Use a spatula to put some metal carbonate into the boiling tube, then feed the delivery tube into position, pour some lime water into the test tube, and then start a timer and immediately begin to heat the metal carbonate, and then record the time when a change first occurs in the lime water. The student repeats the method using different metal carbonates. When a metal carbonate is heated, a reaction sometimes occurs. The equation for this reaction is as we can see here. So when a metal carbonate is decomposed, this is basically thermal decomposition, it produces a metal oxide plus carbon dioxide. This occurs if the metal carbonates can decompose at the lab conditions. We know that actually group 1 carbonates except lithium carbonate, the rest do not decompose at lab conditions. Therefore, they will not break apart like that. So moving on. Here they say, state the name given to the type of reaction. The reaction in which a metal carbonate decomposes into a metal oxide and carbon dioxide is thermal decomposition. You basically use heat to decompose or break apart a substance or a compound. In part B, state 2 variables that the student should control in this investigation. Now, when we go back here, we can see the experiment was repeated with different metal carbonates. So we have to make sure that the amount of the carbonate is actually the same in terms of the number of moles. And we have to make sure that the volume of lime water is the same. So my answer is use the same amount of carbonate and then use the same volume of lime water and use the same size of the solid carbonate. When we talk about the size, we mean the particle size or the surface area of the powder or the particles of the carbonate used. Or you could actually say use powder so that the surface area exposed is exactly the same. Moving on. In part C, suggest why bubbles appear in the lime water immediately after heating has started, but before there is any change to the metal carbonate. If the metal carbonate has no change on it, it means there is no thermal decomposition yet. However, if bubbles are seen in the lime water, it could be because air previously contained in the tube was heated, and therefore that caused formation of the bubbles in the lime water. So I said, when the air in the tube is heated, it expands, and this can create bubbles due to the heated air. Next, I say, explain the purpose of lime water in this investigation. We know that lime water is used to test for presence of carbon dioxide. So I say to test for presence of carbon dioxide, when carbon dioxide is produced, the lime water turns cloudy, and this is proof that the metal carbonate has decomposed. Moving on. Part E says, the table shows some of the results of the student's investigation. So basically, we have a metal carbonate, the color change of the solid, and the time taken for any change in the lime water. So with calcium carbonate, we see it remains white. And again, remember, we know group 2 carbonates will decompose, so remaining white does not mean the decomposition has not occurred. If you look here, the bubbles of gas were formed, or lime water actually turned milky, and that means there was decomposition, even if it took a little bit longer than with copper 2 carbonate. Now with sodium carbonate, it remains white, and there was no change. Because there was no change in the lime water, it means sodium carbonate did not decompose. When we go to copper 2 carbonate, they have not told us the answer here or the color change, but here they've told us the time taken is 50 seconds, and this tells us this reacted faster than that, or it was decomposed faster than calcium carbonate. So here they ask, state the color change that occurs for copper 2 carbonate. Copper 2 carbonate is going to change from green to black because the black color is going to be due to formation of copper 2 oxide, which is this one here. It appears like that, and the green one should be like this. So the color changes from green to black, and they say give a chemical equation for the reaction that occurs. The reaction is copper carbonate breaks down to give us copper oxide plus carbon dioxide. The next part says there is a relationship between the position of a metal in the reactivity series and how easily the metal carbonate reacts when heated. Use the student's results and your own knowledge to deduce this relationship. If you look back in the table and from your memory of the reactivity series, we know copper is below in the reactivity series, and we know sodium is at the top in the reactivity series and calcium is somewhere in between. So we see copper that is below reacted faster, and this one a little bit slower, but this one did not react, which is at the top. So the conclusion is that the lower the metal is in the reactivity series, the easier the decomposition of its carbonate. That is based on the table given. And next they say, state how you should extend the investigation to see if your deduction is correct. To ensure that the conclusion we have made is correct, meaning to know if the lower the metal is in the reactivity series, the faster its carbonate decomposes, we could repeat the experiment using other metal carbonates based on the metals in the reactivity series and see if we'll get the same results. So I said, repeat the experiment using metal carbonates above and below the 3 metals above in the reactivity series. So this brings us to the end of question 5. Let's continue to question 6. Question 6. Zinc reacts with dilute hydrochloric acid to form hydrogen. Give a chemical equation for this reaction. Now we know zinc is a metal, and when a metal reacts with an acid, we get salt as well as hydrogen. So the equation should be zinc plus HCl gives us zinc chloride plus hydrogen. So that is the balanced equation. Next they say, give a test for hydrogen gas. To test for hydrogen gas, we use a lighted splint. This will produce a squeaky pop sound, and that is confirmation that hydrogen gas is present. Part B says, a student investigates the reaction between pieces of zinc and dilute hydrochloric acid. In each experiment, he uses the same mass of zinc, but a different volume of the acid. He collects the hydrogen and measures its volume in each experiment. The graph shows the student's results. So let's see. On the vertical axis, we have the volume of hydrogen in centimeters cubed, And on the horizontal axis, we have the volume of hydrochloric acid in centimeters cubed. Now we can see as the volume of hydrochloric acid increases, there is more hydrogen produced until a specific point. After that, no matter how much we increase the volume of hydrochloric acid, we still obtain the same volume of hydrogen. So let's continue on to the questions. Here they say, use the graph to find the minimum volume of acid needed to react with all the zinc. So if we go back here, again, all the zinc must have reacted at this point. So we go down here to find the volume, and that is 52 centimeters cubed of hydrochloric acid should have been added in order to obtain 120 centimeters cubed of hydrogen. So I wrote 52 centimeters cubed. Next they say, the student repeats the investigation using hydrochloric acid of double the original concentration. If it's double the original concentration, it means it has double the number of moles if the volume is maintained. They say, determine the volume of hydrogen that would be collected using 15 centimeters cubed of this acid, and they want to show you working on the graph. When we come to 15 centimeters cubed of the acid and work upwards to the graph, the volume of hydrogen that must have been produced is 34 centimeters cubed. However, when we double the concentration, it means the volume is also going to double. So 34 times 2 gives us 68. And therefore, 68 centimeters cubed of gas would have been produced. In part C, they say, explain how increasing the concentration of hydrochloric acid affects the rate of reaction. Now, if you increase the concentration, there is going to be more particles of hydrochloric acid in a specific volume, and that means there is a higher chance of successful collisions occurring because a lot of hydrochloric acid particles are going to be within a smaller space. So I said, when the concentration of hydrochloric acid is increased, there are more hydrogen ions within the same volume, and this leads to higher chances of reactants coming into contact with each other, leading to a higher possibility of having successful collisions. Therefore, a higher rate of reaction will occur. Moving on. In part D, the rate of reaction could also be affected by changing the temperature of the hydrochloric acid or by using a catalyst. Explain one other way in which the rate of reaction between zinc and hydrochloric acid can be affected. Now, if we do not use a catalyst or if we do not change temperature, we could change the surface area. Zinc is a solid and it's reacting with hydrochloric acid, which is in aqueous state. It means the surface area should be large in order for the particles to interact well. So I said, since solid zinc is a reactant, the rate of reaction can be affected when the surface area of the solid is increased or decreased. Increasing the surface area can be done by using smaller pieces of zinc, and this would lead to increased chances of particles in contact with each other and therefore a higher rate of reaction. Down here, I put a reminder of the factors that affect the rate of a specific reaction, like temperature, surface area, using a catalyst, concentration, and pressure. So please go through these to remind yourselves of what you should know concerning specific reactions. So this brings us to the end of question 6, as well as to the end of the first part of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.